So the next definition of acids and bases that we are going to use is the Bronsted-Lowry theory. And I'm going to shorthand this as the Bronsted theory simply because it's easier. And in this case, we're going to look at the H plus rather than being produced by an acid and an OH minus produced by the base. We are going to look at an H plus being transferred or donated. So we are going to define an acid as an H plus donor. Now an H plus, remember, is a proton, and we're going to frequently call it a proton donor, and our base is going to be an H plus or a proton acceptor. Now this is a much broader definition of an acid and a base, and note that our H plus, when it goes to our bases are going to have to contain a lone pair of electrons for that H plus to stick to. So the acid molecule is going to give or donate the H plus to the base molecule in our Bronsted-Lowry acid-base theory. All right, for our Bronsted-Lowry acids, our acids are going to be able to donate an H plus. So again, we're going to look for this H plus that can be donated. We're either going to have binary acids, where this H in front can be donated. We're going to have our oxy acids, and remember with our oxy acids here, the hydrogen is attached to an oxygen, and we have some non-oxygen element in the middle, and this could be something like phosphoric, or this could even be like HClO, and this would be a chlorine attached to an oxygen with a hydrogen, and this is the hydrogen that is going to be donated. It's going to come off as an H plus. And remember, our organic acids either contain a COOH group or a OH group where the hydrogen here at the end can be donated. So those are our acids. Our bases for our Bronsted-Lowry theory can accept a proton. So if we have an ammonia and we can add an H plus onto that ammonia, and when we add that H plus onto the ammonia, we are going to make NH4 plus, and because our ammonia can accept that proton, our ammonia is going to be a base because it is accepting a proton. We're going to discuss how in just a second. All right, your strong acids and your strong bases are something you really need to commit to memory, and you need to commit to memory quickly. Our strong acids are our three binary, HCl, HBr, and HI, perchloric, nitric, and sulfuric. Also, chloric is a strong acid, and that's HClO3. So with a quick note on how we do this, for our binary acids, we're looking at group 7, and we're looking at chloride, bromide, and iodide attached to an H plus. The larger the anion is, the more likely this H plus is to come off, and you will make a strong acid. Now, strong means a strong electrolyte, which means 100% dissociated in water. So first of all, these are our strong acids. The other set of strong acids are going to be our perchloric, chloric, nitric, and sulfuric. And please note, as the number of oxygens goes up, the acid strength goes up. So for example, HClO4 is going to be a stronger acid, more dissociated in water, more likely or more ionized in water, more likely to lose that proton than HClO3. So as in this case, the ratio of oxygens to hydrogens goes up. We've got more oxygens to the hydrogens, the acid strength is going to go up. So these are the strong acids. You need to memorize them. Our strong bases are anything that is a group 1 hydroxide with an OH minus, as well as these particular group 2 hydroxides, which are calcium, strontium, and barium with hydroxide. And we know these guys back from our solubility rules, back from chapter 4. Now, some compounds can be both an acid or a base. For example, if you take bicarbonate, and we use bicarbonate in the lab to take and neutralize acids and bases. And if you take bicarbonate and you put it in water, it has two options. It can either lose the hydrogen that it has, or it can gain another hydrogen to go back to carbonic acid. So step one, it could take and make carbonic acid, H2CO3. And when it does that, it leaves an OH minus left over, or it can take and react with water again in a different form, where in this case it's going to act as an acid rather than a base. And when it acts as an acid, it's going to donate the H plus, and it's going to make carbonate plus H3O plus. Now it is amphoprotic or amphoteric, meaning it can go in either direction. So it can be an acid or a base. In this case here, it is an acid, and in this case here, it is going to be a base. Another example on this here, or look at these guys, is water itself. If we take water and we put it with hydrochloric acid donates the proton to the water, making hydronium. And then in this case, we look at our acid-base definitions. And remember that in the Bronsted acid-base definitions, an acid is a proton donor and a base is a proton acceptor. Water here is acting as a base. It is accepting a proton. But in here, if we're looking at water with ammonia and making ammonium, we are noticing that the hydrogen is coming off of the water and sticking onto the ammonia, and water here is acting as an acid. So here, down here, bicarbonate is acting as a base, and here, bicarbonate is acting as an acid. So let's make sure we understand this. Amphoteric means it can act as an acid or a base. And remembering here that an acid is going to be an H plus donor. A base is an H plus acceptor. And with a quick note, one good way to think about water is to realize that if you take an H plus and you stick it onto an OH minus, you are going to make HOH, which is the same as H2O. And so that water is combined of a proton and a hydroxide. And so if we look at water, water can also then break up into an H plus and an OH minus. The water can be an acid and a base. Now, in Bronsted acid-base reactions, whatever original acid or base that we have is going to become the reverse as we go through the process. What do we mean by that? If we consider NH3 plus H2O. We take NH3 and we add it to H2O. NH3, we know, is a base. How do we know it's a base? If it's got a nitrogen, and we say nitrogen and neutral, it's going to be a base here. It's got that nice lone pair on that nitrogen. And when we take and we allow it to react with water, remembering water is an H plus attached to an OH minus, this H plus is going to come over and stick to the ammonia, and we're going to make the ammonium NH4 plus OH minus. Now, ammonia here is a base because it is a proton acceptor. Water here is an acid because it's a proton donor. Now, if this reaction goes backwards, the NH4 is going to donate a proton to the OH minus, making NH4 plus here an acid and the OH minus a base. And what we have here are acid-base conjugate pairs. Conjugate pair is the combination of the base and the acid it becomes, or the acid and the base it becomes. So the acid and the base it becomes is my acid-base conjugate pair. My base and the acid it becomes, again, is an acid-base conjugate pair. So if I have NH3 is the base. The acid that it becomes after it gains the proton is NH4 plus. Water here is a base. The acid that it becomes is H3O plus. And these are our acid-base conjugate pairs out of our reactions. So again, if we take our water here and we look at its conjugate pair, we know that our H2O is our acid and our OH minus is its conjugate base. And our ammonia is our base. And the NH4 plus is its conjugate acid. It is going to be the acid that this base becomes. So if we look at this reaction, we have H2SO4, and it's going to go into HSO4 minus. So we need to identify which one is the acid and which one's the base. So first of all, the one with the more protons is the acid. So as we look at this, as the number of H pluses goes up, or the higher number of H pluses is going to be the acid. If we lose H pluses, we're going to have the base. So if we start out on the reactant side, we're going to have H2SO4. We're going to take off a proton off of that one and make HSO4 minus. This is the acid. This is the base it becomes. We say this is the acid-base conjugate pair. If we look at H2O, H2O as a conjugate, that is H3O plus. Now please note that our conjugates are related by an H plus. The only difference in our acid-base conjugate pairs is an H plus. So if I look at this guy and I look at H2O and H3O plus, the one with the more H pluses is the acid, so H3O plus is the acid and H2O is its conjugate base, or water is the base and H3O plus is the conjugate acid. The acid conjugates go in either direction. We can classify either one as the conjugate of the other. They're simply a pair, and it's a pair related by an H plus. The one with the more H pluses is the acid. The one with the fewer or one less H plus is its conjugate base. So if we took and we considered putting C6H5COOH in water, first thing we have to do is identify whether or not we have an acid or a base. And if we look at this, we see the COOH, and this is going to be an acid. And if we take C6, this is benzoic acid, by the way, H5COOH, and we add it to H2O, the acid is going to donate its H plus onto water. It is going to two arrows, and we'll discuss the arrows in the next section, making C6H5 COO minus plus H3O plus. Our acid-base conjugate pair is C6H5COOH and C6H5COO minus. The one with the more protons is the acid. One with one fewer proton is the conjugate base. Water here is a base, and H3O plus hydronium is the conjugate acid of water. We can do this in other interesting cases. So let's imagine that we have F minus reacts with H2O to make HF plus OH minus. So if we look at these and we try to relate our pairs, we know that they're related by an H plus. So one pair is F minus HF, and the other pair is H2O and OH minus. We know the one with the fewer protons is the base, so F minus is the base, and HF is the conjugate acid. In the case of water, it is the acid, and OH minus, having one fewer H plus, is its conjugate base.